Hello. In the lesson right before spring break, you learned a little bit about cladograms as part of our evolution unit. And I'm going to start with a quick review in the form of a short video because today's main event is a gizmo activity to help you further understand how we build cladograms.
Have you ever organized your room and realized that you put similar or related objects near each other and completely different objects farther away? This is similar to how scientists construct a cladogram. Cladistics is a systematic method of classification which uses shared derived characters to make a cladogram. A cladogram is a branching diagram that represents the proposed phylogeny or evolutionary history of a species or group. Cladistics assumes that each group has an ancestor that other species do not share. The cladogram in our example shows how 4 very different species could develop from a common ancestor. The common ancestor would be at the bottom of the diagram. The cladogram is constructed by sequencing the order in which the derived characters evolved with respect to the outgroup. The outgroup is the species that has more ancestral characters with respect to the other organisms being compared. In this example, mollusks are the outgroup. The closeness of the clades in the diagram indicate the number of characters shared. The group that is closest to echinoderms shares the most derived characters with echinoderms, and shares a more recent common ancestor than with groups farther away. Each line that breaks away from the main line is called a node. The nodes where the branches originate represent a common ancestor. Thus, echinoderms and arthropods have 3 derived characters in common, so they share a more recent common ancestor than echinoderms and mollusks. Now you see how scientists organize species based on shared characters, similar to how you organize your pens and pencils, together, separated from your awesome collection of music.
So let's assume we have 3 organisms and we're going to call them A, B, and C. These 2 diagrams represent 2 hypotheses indicating possible evolutionary relationships. So we're asking the question, what does each tree tell us about organisms A, B, and C? So tree 1 indicates that B is more closely related to A than it is to C because A and B are closer together. And tree 2 indicates that B is more closely related to C than it is to A. But without more information, these hypotheses remain equally valid. So now you're given some additional information. You are told that characteristic 1 is found in organism A only, and characteristic 2 is found in organism B only. Characteristic 3 is found in organism C only. But characteristic 4 was found in both B and C, but not A. This is a key piece of additional information. So we're going to add this information to the diagram using a simple line, which I've color-coded purple. I'll show you how that works. So just to review what we just said, characteristic 1 is found only in organism A. Characteristic 2 is found in B only. Characteristic 3 is found in C only. But characteristic 4 is found in both B and C, but not A. There's 2 different ways we can indicate that. One way on tree 1 and one way on tree 2. So both of these trees display all of the information I just read from the previous slide. But if you look closely, they're drawn a little bit differently. In tree number 1, we have characteristic 4 drawn with the purple line right at this point. And it's showing that it's common to organism B and C, but not to A. Over here, we have characteristic 4 drawn at 2 different locations, but it tells us the same thing. So which hypothesis do we accept, or do we accept them both? That's where we're going to introduce a new word. It's called parsimony. And the parsimony principle says that the most likely solution is usually the simplest. So what do we mean by the simplest solution? It's the solution that accounts for all of the information but requires the fewest evolutionary changes. That's likely the way it happened in nature. So if we look at these two solutions again, they're not identical, and one definitely provides a simpler solution because it has fewer evolutionary changes. So I think everybody can see that tree number 1 is simpler. Characteristics 1, 2, and 3 don't help us here in making this decision as to which hypothesis is the simplest. But characteristic 4 needed to evolve twice in this diagram right here. See, it needed to evolve here and it needed to evolve here. But it only needed to evolve once in this position in tree number 1. So tree number 1 is the simplest solution, and we could also say it's the most parsimonious. Oh boy, that's a hard word. As only 4 evolutionary events needed to happen in tree number 1 versus 5 events. 1, 2, 3, 4, 5. I know the number 4 is cut off here, but there's a number 4. So tree number 1 is the hypothesis we accept. In the gizmo you're about to do, it will calculate a parsimony score for you. And that's going to tell you how many evolutionary changes have occurred in a given cladogram. The lower the score, the more likely the solution, and the more likely we accept that cladogram as the solution. So just to sum things up, and now you can see the number 4 over here is not hidden by my face. Which hypothesis do we accept? We accept this hypothesis because it is the simpler cladogram showing characteristic 4 only evolving once versus twice. We're not going to watch this video together, but there is a link in Schoology, and the Bozeman guy does an excellent job of giving you an example of how you would build a cladogram. I recommend you watch this at least once before tomorrow's assessment, but maybe twice, and you can pause and rewind as needed. So now I'm going to ask you to go to explorelearning.com and put in your password and launch the cladograms assignment that I've loaded in for you, and we're about to preview document 14.1 together. So please have 2 tabs open, one for the gizmo activity on Explore Learning, and one with your 14.1 gizmo document, which will be due by midnight tonight. But we'll preview it together and get started together.